Hey folks, this is Chris Kornman, Lab and Education Manager at the Crown, and welcome to the physical analysis of green coffee. The physical analysis of green coffee can be broken down into four basic categories: size, density, water content, and defect count. Each of these metrics can have a bearing on any coffee's sensory quality and trade value. As such, it's worth the time of any roaster, coffee buyer, importer, exporter, processor, and farmer to have at least a cursory understanding of these important measurements, how they can be obtained, what their causes and effects might be, and to what degree they might be improved upon. Over the next few pages, we'll seek to cover both introductions to broad concepts and to dive deeply into misunderstood corners and clarify complex concepts in order to demystify the physical analysis of green coffee. This is chapter 2 of 4 in our series on green coffee analysis. And we'll be covering density today. The other chapters include screen size, moisture and water activity, and physical defect count. If you're interested in further reading, our blog, royalcoffee.com/blog, has a number of really interesting educational materials. Today's session will cover the density of green coffee. Our first topic will be defining our terms, and then we'll look at how density can be measured. I'll offer some tips and tricks for doing it in your own labs or at home. We'll also investigate how coffee is sorted for density in producing countries, and look at some global trends. And finally, we'll investigate both the financial implications of high and low density green coffee, as well as the roasting and qualitative implications. Density is a fairly straightforward mathematical concept. It is the mass of a given object divided by the volume that it takes up. That is, how much stuff fits into a given three-dimensional physical space. An example of this might be how much green coffee fits into a jute sack, or how much roasted coffee will fit into the bags that you're selling at retail on the shelf, for example. In the metric system in a perfect environment, that is room temperature, sea level, etc., 1 gram of water, that's the mass, will fill exactly 1 milliliter of space, that's the volume. So water has a density of 1 gram per milliliter. As far as measuring green coffee's density in the lab setting, there's essentially two practical methods of measurement. The first would be displacement, and you may recall the story of Archimedes of Syracuse, who was tasked with trying to ascertain whether or not the crown that had been given to a king as a gift was in fact pure or impure gold. And frustrated by his inability to figure this out on his own, he decided to relax at the baths, and his bathtub had been filled to the brim, and when he stepped into it, the exact amount of water that his body would have taken up was displaced out of the bath. And of course he jumped up and screamed Eureka. And this principle of displacement can be applied to any physical substance, green coffee included. So to do this in your lab setting, weigh your coffee first, and then measure a known quantity of water into your graduated cylinder, let's say 30 or 40 milliliters, for example. Once you know your level of water, add the green coffee to that water level, and then measure the new level at which the water has been displaced to. So let's say you add 20 grams of coffee and it displaces your water by 25 milliliters. You would need to take that differential into account. So either subtract your new figure from the original volume of the water, or simply take the difference of the two. It's the same. And then using that new figure, your new water level differential, divide the weight of the coffee by that water differential, and that will give you the density of your green coffee. The other measurement is a little easier to do, although it will give you different results, and we'll dive into that in just a second here. But the other measurement is called free settling. It's also known as free flow or bulk density. And in this instance, we're not going to be using water. You just weigh your coffee first and then add the weight to a graduated cylinder and measure the volume that it fills up to whatever line it is, and then simply divide the weight by the new volume. So what are the pros and the cons of these two different measurement methods? Well, for displacement, it allows for a high degree of mathematical precision and theoretically is exactly accurate. We know this because it accounts for the empty space between the beans, and so you're obtaining a true scientific measurement of the density of the coffee. However, if we're using the free settling method, the measurement process is relatively easy and we don't risk the loss of our measurement material. That is, we're not making that coffee wet and potentially rendering it useless. Free settling also has an interesting application in that it reflects storage conditions. That is to say, it accurately represents real-life behavior, and therefore is recommended by the International Standards Organization. If you think about this practically, in a theoretical sense, if you're measuring your green coffee's density using displacement, you might be able to fit 70 kilos of coffee into a 60-kilo jute sack, but we know that that isn't necessarily possible because displacement does not account for, or displacement accounts for the empty space between the beans, which will not behave like that in a real-world scenario. So let's solidify this principle by looking at a real-world example, measuring two different coffees using both the displacement and the free settling method. I've selected a Ethiopian grade 1 washed coffee as our high density example, and a wet hulled Sumatra, also a grade 1 in prep, but much lower density for our second example. So let's take a look real quick at the displacement figures first. On the right here, you'll see that we have started with a known quantity of coffee. Our mass has been measured in advance, and we measured an exact figure for our volume of water, and then the coffee, when added to the water, displaced it up to this figure. So we took the difference of this number and obtained our differential in water volume. That's the displacement volume. You can then divide this number by that number, and what it gives us is our final density, that is in grams per milliliter. And so we can see that in both cases, the Sumatra and the Ethiopia, they are measuring at slightly over 1 gram per milliliter, which means that they are in fact slightly denser than coffee and or slightly denser than water. And we can confirm this by knowing whether or not it sinks in water, right? If it's above 1, then it should be sinking in water because it is more dense. In our second example, in the free settling method, the airspace between the beans results in a range that's much lower. So we've taken, and in this case, what I usually do is take an average of 3 measurements for myself. So the Ethiopia, once again, is measuring at a higher density level, but it is significantly below the measurement that we obtained using displacement. Typically, I expect to see measurements of that like 0.6 to 0.7 grams per milliliter. So this is to illustrate a couple of things. Adding water helped to accurately assess true density, but it isn't really a great storage method for coffee, and you'll have to be willing to sacrifice some green. In terms of absolutes and theoreticals, displacement's more accurate, but in terms of real-world behavior, free settling is more appropriate. So in a sense, they're both the right way to do it. It just depends on the results that you need to obtain. The point to take away from all this is that if you're consistent with your methods, you should be able to observe data that are meaningful, regardless of whether you're free settling or displacing. Okay, so now that we understand how to measure density in our labs and what it actually means mathematically, let's take a look at how density is sorted at origin. Before coffee is exported, it will nearly always undergo density sort at least once at the dry mill. Additionally, in many cases, parchment and even cherry density sorting may take place, depending on our location and our processing method. So let's start from the beginning. In some countries, particularly places like Rwanda and Burundi, who continue to struggle with eliminating potato defect, coffees can be separated by density before they're pulped and fermented. This adds a layer of quality control before the coffee processing even begins. Farmers bringing the day's harvest of coffee cherries will simply drop their cherries into a net and then lower them into a bucket or a tank of water. Any floaters, those coffees of low density, are removed, and all the high quality dense coffee is then sold to the washing station for processing. This is a really effective method of sorting out the most egregiously low density or damaged coffees before pulping. That way, at the processing, all the coffees of similar densities would be processed together as opposed to having to sort them out separately later. This is frequently employed as a potato defect mitigation step in Rwanda and Burundi. It's often easy to identify those insect-damaged coffee cherries by floating them first. It's one more step that a conscientious producer can use to increase the quality of their coffee. Basically, all fully washed coffees will undergo density sorting immediately after fermentation. Moving depulped coffee parchment through narrow channels of clean flowing water, which is the actual wash in the washed processed coffee. Anything that floats, usually the hollow seed, can be separated from the higher grade parchment that sinks. In many cases, up to 3 quality tiers can be delineated by this process, and the slowest, heaviest, densest coffees tend to taste the best and sell for the highest price. If you look at the picture on the right of this image, you'll see on the left side is the fermentation tank, and the gentleman at the forefront is pushing the last of the coffee from that fermentation tank down through this tube, which will then feed into the grading channel. And then these workers here are pushing that dense coffee, the heavy stuff, along the grading channel. This serves to remove a lot of the fermented mucilage and clean the parchment itself. They're using quite a bit of water in this process, and as it flows through this channels down over these different little barricades here, the floating coffee will go down first above it and be separated out later, and then the most dense coffee will be the last to move. We'll take a look at a video of this so you can get a better sense of how it works. So what we're observing right now is the lowest density coffees moving over one of those barricades. And then these workers here are pushing the more dense coffee along through the channel. That pushing process is what in part accounts for removing the fermented mucilage. And then right here he's stopping anything that's sinking from making it all the way down here into the first separation. That's the lightest coffee, the lowest grade. What we're left with is our high-density coffees back up at the top of the channels, which must be pushed along with a fair amount of effort. You can also see clearly this takes a significant quantity of water to produce. Lastly, even coffees that are not washed will be sorted by density at the dry mill. Using vibrating tables with grooved surfaces set at a slight angle, low-density material like broken beans, hollow shells, dry parchment, and even foreign objects can be removed. While fickle, a properly calibrated density table can sort down to a preset number of defects in many cases. Conversely, poorly calibrated tables can lead to excessive defect counts, low cup quality, and/or roasting defects. As with screen size, a second pass through these machines can increase the accuracy and precision of the defect sorting. While there are plenty of exceptions, density often varies from place to place in some predictable ways. East African coffees, particularly those from Ethiopia and Kenya, tend to register very high on the density spectrum, as do coffees from Colombia, and as I've noted in some recent crown jewel analysis, coffees from the Catracha project in southern Honduras. Conversely, coffees from places like Sumatra and Brazil tend to generally be pretty low density by comparison. Yemen might fall into that category as well. High elevations and smaller screen sizes tend to be denser than low-grown and large seeds, but there's plenty of exceptions to this. Washed Central American coffees tend to trend towards the middle of the spectrum, while natural coffees often tend to be less dense than their washed coffee counterparts. Also, contrary to popular opinion, wetter coffees are less dense than dry ones, and we'll get into a little bit more detailed examination of that in just a second. So here are some common measurements that we take, and I've represented them both in grams per liter in the text and also in grams per milliliter on the chart. These are the exact same figures, except that it's just a multiple of 1,000. So that's the difference between a milliliter and a liter. And what we generally see across the board for these free settled measurements of green coffee is that anything below that 0.66 or 660 grams per liter measurement tends to be what I would consider well below average. It's the 670 to 690 range that tends to be our sort of average range, whereas anything above that 700 grams per liter mark is definitely well above average. These are based on observations of about 4 years worth of crown analyses of a couple hundred different coffees using both the manual and a method on the Cynar Bean Pro. The moisture meter actually is calibrated to the ISO standards and spits out a figure that's in most cases very close to what we're measuring by hand in the lab. It's not hard to infer from the sorting techniques employed post-harvest that a coffee's density matters. The implications are interrelated with its quality in the cup and its value on the market, so let's talk finances first. Remember that old grade school riddle, which is heavier, a pound of feathers or a pound of lead? Well, the answer, of course, is that they weigh exactly the same, a pound. It's the density that's different. A pound of lead is significantly denser and therefore takes up less space. You're going to need a whole lot more feathers to accumulate to a pound. Likewise, a 60 kg bag of low-density coffee weighs exactly the same as a 60 kg bag of high-density coffee. The difference is that it takes more low-density coffee beans and more space to equal that 60 kg. Consequently, higher density coffee is more valuable. If you're filling a three-dimensional space like a fermentation tank, a drying table, a jute bag, a shipping container, a warehouse shelf, a storage bin, etc., you'll fit a heavier load of coffee into that space if it's higher in density. It's more efficient for both storage and transit. Each high-density coffee bean that's picked, processed, and sorted is more valuable because it weighs more and or takes up less space than a similar bean of low density. So let's take a look at a mathematical example using our Sumatran and Ethiopian coffees from before. To fill a 60 kg bag of Ethiopian coffee beans of higher density, will require about 88.2 liters of space. To fill the same weight with the lower density Sumatra, you'd need 93.8 liters of space, which is 6.3% more Sumatran coffee that you'd need to fill that bag, which is kind of a lot. In this scenario, Sumatran coffee farmers would have to pick 6.3% more cherries, and because the Sumatran coffee in our example takes up 6.3% more space, it might in fact be more expensive to ship if a given container maxes out on space before hitting its weight limit, for example. Another revelation that I stumbled on while I was doing research for this a couple of years ago, and you might have already guessed it, we've mentioned it once or twice already, but the fact is that higher moisture content in green coffee is going to equal lower density. Aside from the practical concerns of quickly selling coffee that's not completely dry, sometimes I think that coffee producers and exporters might be unfairly accused of shipping wet coffee because there's the perception that it might be heavier and that coffee trades on weight rather than volume. I think the line of thinking here is that because it's full of water, maybe it weighs more and therefore might be more valuable. But if you recall how we discussed that using the displacement method, the true density of coffee is actually higher density than water. It means that cup quality notwithstanding, there's negligible value to be added by shipping wet coffee. To demonstrate this, I surveyed 50 recent crown jewel analyses, and a trend began to emerge. I cross-referenced the moisture content with the density measured by free settling. And as the density increases from left to right on the chart, the moisture tends to trend downward to the tune of about 1% for every 0.04 grams per milliliter. So I think the takeaway here is that for the producer, shipping wet coffee is faster. You can get it off those drying tables more quickly and clear up space. But ultimately, that coffee is going to be of lower density and overall of lower value. And we'll get into the implications of moisture content in the next session. Um, However, conversely, drying coffee well has positive implications for both the quality of the product as well as the overall profit. One other example to demonstrate this point is when I was working through these numbers, I actually remembered that I had access to a single coffee that was shipped in two different packaging types. And when it arrived, those two different packs, the one was a jute bag and one was lined with Grain Pro, they arrived with different moisture content. And therefore I figured out that I could test this mathematical trend on an actual real coffee. So at the time of the experiment, the sample packed in Grain Pro read 11.4%, while the jute sample was a little bit higher at 12.1%. So about a 0.7% difference in moisture content. Not a huge difference, but enough to be able to get some measurements on. Over a number of freely settled measurements and a couple of displacement measurements, on each coffee, the drier Grain Pro was measured denser overall than the wetter jute coffee by a little over 2%. And so what I think that this demonstrates is that even though this was just one quick observation, having the same coffee preserved at these two different moisture readings gives me some confidence, reiterating the fact that the general trend is going to hold true, that in the most common situations, dry coffee is going to be denser because its makeup is a higher ratio of the solids of coffee to the water that's been preserved within it. Wetter coffee is going to lose a higher percentage of its weight during storage and transit and roasting as well, which further decreases its overall value. So let's talk density and roasting. In my experience, the densest coffees tend to react uniquely to heat application in the roaster, which has implications for sensory quality as well. Most high-density coffees are going to require additional heat energy to power through the Maillard browning reactions and into first crack. If a low-density coffee is like cooking with a stainless steel skillet, then a high-density coffee might be like cooking with cast iron. It's going to require more energy to get up to temperature, but once it's there, it might also conduct that heat energy better. Low-density coffees tend to progress fairly easily through the early stages of roasting and generally speaking are going to require a more gentle touch once first crack starts. High-density coffees, however, shouldn't get blasted with heat immediately, in my opinion. This will merely scorch the outside without penetrating the interior of the beans. Rather, in my opinion, high charge temperatures might help, but using that high charge temp but a low gas setting, and then gradually increasing through the earliest stages of roasting might be a better way to provide sufficient thermal energy to gently but firmly accelerate the coffee into first crack. At this point, the highest density coffees will often experience a dip in their delta, or rate of rise. And the careful roaster will need to navigate the tricky in-between of stalling and baking the roast versus overzealously applying heat and burning off any acidity and sweetness at this critical point in the roast. Once a solid 70 to 90 seconds of defined first crack have occurred, the rate of rise will usually recover, and you should be able to confidently back off heat application if your desire is to move beyond this level of color and still preserve some sweetness and acidity. So just to recap there, usually when you hit first crack with a high density coffee, the delta is going to dip and you're going to need to make sure that you've got enough energy to progress through the first crack without stalling out. So what all this might mean in terms of the resultant flavors is somewhat general and obviously is going to be affected by the availability of characteristics in your starting materials. You're unlikely to turn a past crop leftover into a floral candy flavored sweet coffee, no matter how carefully you're roasting. That being said, a few generalities I think can be suggested at here. I tend to find that the densest coffees have brighter and more complex acids and raw, more sucrose-like sugar flavors than the lower density counterparts. It's of course a very broad stroke of the brush, and I wouldn't take this as a hard or fast rule, but in many cases I think that that's kind of what we see, and I wonder sometimes if that is related to those high density coffees also being, in some cases grown at the highest elevations, and therefore having those slow cherry maturation time frames, which increases the available sugars to the roaster. All right, thanks for joining me today for this session on density in green coffee. Hopefully we learned some stuff that we can take back to our roasting facilities and our green grading labs and be able to apply. I think that density of coffee specifically is maybe one of the easiest and most useful pieces of information to ascertain when it comes to the quality of your coffee. And the equipment investment is minimal. You can do it with a paper cup if you have to. So if you have questions about this topic or any others, feel free to reach out to me at ckornman@royalcoffee.com. And then please do join for the next couple of sessions on this topic. We'll be covering moisture content and water activity in the 3rd chapter, as well as physical defects in the 4th. There's plenty of available resources online at royalcoffee.com if you're interested in more educational opportunities there as well. So thanks and happy roasting.